Let A1, A2, A3, A4, A5, A6 be a hexagon inscribed inside a circle of radius r. Furthermore, for each positive integer I, let mi be the midpoint of the segment ai plus 1, where a7 equals a1. Suppose that hexagon m1, m2, m3, m4, m5, m6 can also be inscribed in a circle. If a1, a2 equals a3, a4 equals 5, and a5, a6 equals 23, then r squared can be written in the form m over n, for relatively prime positive integers m and n. What is m plus n? We have hexagon a1, a2, a3, a4, a5, a6, and it can be inscribed in a circle of radius r. We're also given that the midpoints of its sides, which are m1, m2, m3, m4, m5, and m6. The hexagon formed by connecting those points, m1, m2, m3, m4, m5, m6, can also be inscribed in a different circle. And we need to find the value of r if a1, a2, and a3, a4 are equal to 5, and a5, a6 equals 23. It seems like this problem has a lot to do with hexagons and being inscribed in circles. And so that tells us we'll need to work with the angles here. So let's turn the condition hexagon is cyclic into an angle condition we can actually work with. So let's copy paste this hexagon a1, a2, a3, a4, a5, a6 and see what conditions need to be true in order for this hexagon to be cyclic. If you notice here, any cyclic hexagon can be split up into two cyclic quadrilaterals. In this case, a1, a2, a3, a4, a5, a6 can be divided by line a3, a6. And line a3, a6 splits it up into two cyclic quadrilaterals, a1, a2, a3, a6, and a3, a4, a5, a6. And in each of those cyclic quadrilaterals, the sum of opposite angles is equal to pi. So angle a2 here plus this part of angle a6 is pi, but also equal to pi is this angle here plus angle a4. So it's clear that each pair of angles I've marked with the same color has sum equal to pi. The gray angles have some pi, and the cyan angles have some pi as well. So if we sum them, we get angle A2 plus angle A4 plus angle A6 in this hexagon is equal to 2 pi. And that's true for all cyclic hexagons, A1, A2, A3, A4, A5, A6. We have angle A2 plus angle A4 plus angle A6 is equal to 2 pi. Let's use that here. In this hexagon here, we have its midpoints, M1, M2, M3, M4, M5, M6, and those midpoints create 6 triangles. We have to work with the angles in those triangles, which can help us determine the angles of the original hexagon as well as the angles of the midpoint hexagon. So let's start by denoting this angle here, A1, M6, M1, as angle U. Now, what else is U equal to? Well, M6, M1 will get sent to A6, A2 if we do a scale factor at A1 with ratio 2. Because M6, M1 is the midline in triangle A1, A6, A2. So if we do a scale factor at A1 with ratio 2, M6, M1 is going to get sent to A6, A2. And therefore, this angle here is also equal to U. So that's equal to U. Now, what else is that equal to? Well, if you see here, angle A1, A6, A2 is also equal to angle A1, A3, A2 because they both cut off arc A1, A2. So this here is also equal to U. And doing a scale factor now at A2 with ratio 1/2, that's going to bring A1, A3 to M1, M2, the midline in triangle A1, A2, A3. So angle M1, M2, A2, that's also going to be equal to U. And a similar logic applies to every other triangle as well. So we can label this continuing in this series of triangles. The 1, 3 ahead is always going to be the same. So this is also going to be V, W, W, X, X, Y, Y, Z, and Z. So we found all the angles in the 6 triangles that are not equal to an angle of the original hexagon. But we can use the triangle angle sum equal to pi to find the angles of the original hexagon. And we can also use the sum of the angles along a line is equal to pi to find the angles of the midpoint hexagon. So finding all 12 of these angles has now allowed us to determine both the angles of the original hexagon and midpoint hexagon. So for the original hexagon, we see that angle A2 plus A4 plus A6 is equal to 2 pi. And angle A2 here is equal to pi minus u minus v, because it's the remaining angle in a triangle, 2 of whose angles are equal to u and v. This triangle here, A4, that's pi minus w minus x. And A6, that angle is going to equal pi minus y minus z. And if we add these, we're going to get that angle A2 plus A4 plus A6, 2 pi, is equal to 3 pi minus u plus v plus w plus x plus y plus z. And so pi equals u plus v plus w plus x plus y plus z. Okay, now what else? Well, we have angle M2 plus M4 plus M6 is also 2 pi, because that hexagon can also be inscribed in a circle. So angle M2 is pi minus u minus w here. Angle M4 is pi minus w minus y. And angle M6 is pi minus u minus y. So if we look here, we have that angle M2 plus M4 plus M6, which is 2 pi, is equal to 3 pi minus 2 times u plus w plus y. If you see, each of u, w, and y appears twice here. U twice, w twice, and y twice. So if 2 pi is equal to 3 pi minus 2 times that sum, then pi is equal to 2 times u plus w plus y, giving u plus w plus y equals pi over 2. Now, if pi was equal to u plus v plus w plus x plus y plus z, then pi over 2 is equal to both u plus w plus y and v plus x plus z. So we found that both angles u plus w plus y and v plus x plus z sum to pi over 2. Now, how can we connect that with the other info that's given in the problem? We have that A1, A2 equals A3, A4 equals 5, and A5, A6 equals 23. And we would like to find the value of r squared. So let me just delete everything else but our key finding, which is that u plus w plus y and v plus x plus z are equal to pi over 2. Okay, if A1, A2 is equal to 5, then what must be true about the angles? Well, we see that angle A1, A6, A2 is equal to angle A1, M6, M1, because M6, M1 is a midline and triangle A1, A6, A2 is just a simple scale factor with ratio 1/2. And angle A1, M6, M1 is equal to u. So this angle here is equal to u. And by using the extended law of sines, we know that A1, A2 over 2 sine u is going to equal r. So 5 over 2 sine u is equal to r. So what's u? Well, we have sine u is equal to 5 over 2r. So u would be the arcsine of 5 over 2r. Now let's use the extended law of sines on triangle A3, A2, A4 to find A3, A4, which is 5 in terms of R. Well, angle A3, A2, A4, through a similar logic as A1, A6, A2, using the midline is going to equal W. So 5 over 2 sine W is equal to R. And so W is equal to arc sine 5 over 2R as well. And now for the final one, we have that A5, A4, A6 is equal to Y by using the midline once again. These angles here are going to equal each other. So angle A5, A4, A6 is equal to Y. Therefore, A5, A6 is 23 over 2 sine Y is equal to R. And that means that Y is equal to arc sine 23 over 2R. So now we have the values, the exact values of U, W, and Y in terms of R. Now let's use this to create our equation in terms of only R and arc sine. So we have U plus W plus Y is pi over 2. Let's use a different color. U plus W plus Y, that's 2 arc sine 5 over 2R plus arc sine 23 over 2R is equal to pi over 2. Now, I suggest moving this arc sine 23 over 2R so that it's on the same side as pi over 2. So it would become arc cosine 23 over 2R then. 2 arc sine 5 over 2R equals pi over 2 minus arc sine is arc cosine. So arc cosine 23 over 2R. And now we have to sine both sides. So if we sine 2 arc sine 5 over 2R, we're going to get 2 sine cosine, which is 2 times 5 over 2R, times the square root of 1 minus 5 over 2R squared. And that's equal to the sine of arc cosine 23 over 2R, which is the square root of 1 minus 23 over 2R squared. And now, if we multiply both sides by 2R, we're going to get 2 times 5 over 2R, which is just 5 over R, times this times 2R, which is just the square root of 4R squared minus 25. And the right side times 2R, which is the square root of 4R squared minus 529. And now we have to multiply by R. 5 times the square root of 4R squared minus 25 equals R times the square root of 4R squared minus 529. So now we have to square both sides to get rid of the square root. We have 25 times 4R squared minus 25 is equal to R squared times 4R squared minus 529. 100R squared minus 625 equals 4R to the 4th minus 529R squared. Now we subtract 100R squared minus 625 from both sides. We get 4R to the 4th minus 529R squared minus 100R squared would be 629R squared plus 625 equals 0. And we see this can be easily factored right away. We know it's equal to 4R squared minus 625 times R squared minus 1 equals 0. So R squared is either equal to 625 over 4 or it's equal to 1. But if R squared is equal to 1, then R would have to equal 1. And there's just one problem. We can't have a chord of length 23. Like A5, A6 is 23. That cannot fit on a circle with radius 1. Not even 5 can fit on a circle with radius 1. The largest possible chord that could be on a circle of radius 1 is 2, and that's only the extreme case when it's a diameter. So r squared cannot equal 1. It equals 625 over 4. And if r squared is equal to 625 over 4, just to verify that this is indeed correct, we would have r equals 25 over 2, and the largest possible chord that could fit on that circle would be of length 25 when it's a diameter. And 23 is within those bounds. That's the largest length given here, 23. So we can be sure that the answer is correct. R squared equals 625 over 4. And it can be written in the form m over n for relatively prime positive integers m and n. M equals 625 and n equals 4. Find m plus n. It's 629. And we are done. Thank you for watching this YouTube video. And please follow my channel if you would like to see more videos. Let's get to 375 followers before the AIME I on February 1.